Hello and a warm welcome to the AI with Arun show. In this episode, we are diving deep into perhaps the biggest technological power struggle of the decade, the war for AI compute. Imagine a kingdom where one company, Nvidia, has ruled supreme for over 10 years, controlling the very foundation of the AI revolution. This is not just a small kingdom. The global AI hardware market is projected to eclipse $400 billion by the end of this decade. For years, we have lived in an AI world built on an Nvidia monoculture. But a structural threat has just crystallized, signaling a fundamental restructuring of the entire AI supply chain. Our story begins in late 2025 when a massive alliance forming Meta, Google Cloud, and Oracle Corporation. This convergence challenges the fundamental assumption that Nvidia will maintain its dominance forever. This is the moment that the giant is challenged. Now, before we meet the challenger, we must understand the incumbent's fortress. Why has Nvidia been so dominant? They didn't just sell chips, they built a full stack platform that combines silicon, networking, and crucially, software. At the heart of the GPU is something called the SIMT architecture that stands for single instruction, multiple threads. Think of it like a massive army. One command is given, and thousands of soldiers or threads execute it simultaneously. This architecture, which started in gaming, gives the GPU incredible versatility. NVIDIA's chips, like the H100, can handle almost any type of calculation thrown at them, from dense math to physics simulations. They build specialized units called tensor cores to specifically handle the mixed precision math required by deep learning. This versatility means NVIDIA is a safe choice for researchers everywhere. Finally, there is a supply chain moat. NVIDIA secures the lion's share of specialized packaging capacity called COWOS TSMC. By monopolizing this critical step, they constrain the ability of competitors, including Google, to produce chips at scale. They control the flow of goods, maintaining scarcity and high prices. Now let's meet the alliance determined to crack this fortress. This is not a simple purchase, it's a tripartite alliance designed to break the vendor lock in. Now, vendor lock in is simply being stuck with one supplier. Meta, who needs billions of dollars of chips, does not want to be locked into paying Nvidia's tax. Reports indicate that Meta is in advanced negotiations with Google to lease and potentially deploy Google's custom silicon, the Tensor Processing Unit, or the TPU, directly within its own data centers. And where does Oracle fit in? Oracle Cloud Infrastructure, or OCI, acts as the Switzerland of cloud computing. Meta already uses Oracle for training its massive Llama models. This means OCI can act as an orchestration layer connecting Meta's existing infrastructure with Google's new TPU power. This makes the whole migration process much smoother for Meta. Meta's strategy is elegant and aggressive. It's a two-phase plan that defies typical cloud models. Now, phase 1, 2025-2026, is the rental bridge. Meta will immediately lease massive amounts of the latest TPUs, the Trillium and the Ironwood chips via Google Cloud. This lets them immediately offload Llama training and inference workloads. They can test the chips and software without buying them yet. In phase 2, which is 2027 onwards, is the on-prem transformation. This is the most disruptive part. Meta wants to purchase the TPU silicon outright for deployment in their own data centers. Historically, Google has guarded TPUs as a differentiating asset. This move breaks that precedent. This hybrid model gives Meta supply chain sovereignty. It allows them to control their own hardware, mitigating shortages and gaining deep control over the thermal and electrical engineering, which are the dominant cost drivers in the AI era. So we have now established the why. Now let us look at the what. The TPU is not a modified graphics card. It is a domain-specific architecture built purely for the math of neural networks. The core strategy or the core difference is the systolic array. You may have heard of the von Neumann bottleneck, which is the problem of constant data fetching from memory that GPUs face. TPUs solve this with systolic array. Think of it like a high-efficiency assembly line. When running a calculation, the weight parameters, meaning the knowledge of the AI model, are loaded once and stay stationary. The data which is your prompt or activation data, then flows rhythmically through the array, passing partial results sequentially. So, why is this such a big deal? It's all about efficiency. This rhythmic flow drastically reduces the need to constantly access memory, which saves vast amounts of energy. This gives TPUs a dark silicon advantage, often resulting in a 2x to 3x better performance per watt for dense matrix math compared to GPUs. They do the job for less electricity. The rivalry is now heating up between Google's 7th generation chip, Ironwood V7, and Nvidia's Blackwell, which is B200. Historically, Nvidia had the memory advantage, but that is changing. The jump to Ironwood is crucial because it matches Blackwell in high bandwidth memory, HBM capacity, which is 192 gigabytes or GB. Since the largest AI models like Llama 4 are often limited by memory, how fast data can be moved, this parity neutralizes one of NVIDIA's key structural advantages. While Blackwell promises enormous raw throughput, especially using sparsity, Ironwood is explicitly marketed as an inference focused chip. This means it is optimized for serving models to users, not just training them. In the world of supercomputing, connecting the chips is as important as the chips themselves. This is where Google has a distinct advantage in scale. NVIDIA relies on copper NVLink cables within a rack, which is fast but limited in distance, connecting up to 72 GPUs in a single unit. However, Google uses an optical circuit switch OCS system. This system uses tiny mirrors to switch beams of light. This allows them to dynamically reconfigure the network topology in milliseconds. So, what's the result? Scale and resilience. Google can connect up to 9,216 chips in a single massive pod with low latency. Crucially, if one chip fails during a massive training job, say training Llama 4 Behemoth, the OCS can immediately route around the failure, protecting the expensive months long job. This fault tolerance is a strategic asset for the biggest players. Now, choosing between a GPU and a TPU is not about which one is better overall. It's about the workload suitability. For training, particularly when developing a new model architecture, NVIDIA remains the same safe, flexible choice. The versatility of the CUDA software that NVIDIA has lets researchers experiment easily. But the real money threat is in inference. Inference is the process of serving the model. When you ask an AI chatbot a question, that is inference. Meta serves billions of users on Instagram and WhatsApp. The cost of running that service is an operational nightmare. Google's Ironwood is designed specifically for this factory AI scenario. The systolic architecture delivers much higher throughput for batch 1 or small batch inference, the kind of real time requests typical of chat. A single Ironwood chip can hold Metalama's 4 Scout model and its massive context window, potentially serving more concurrent users than an H100 for a fraction of the energy cost. This is where billions in savings are found. NVIDIA's single strongest defensive advantage is not the hardware, it's the software moat, the CUDA, which stands for the Compute Unified Device Architecture, CUDA, CUDA. Now, CUDA has a 15-year head start and is the lingua franca, which is the universal language of accelerated computing. Developers love it because it allows them granular control to optimize their code. Google and Meta are trying to breach this mode using PyTorch XLA. Now, PyTorch is the framework Meta uses, and XLA, which stands for Accelerated Linear Algebra, is the intermediate language for TPUs. PyTorch XLA acts as a translator, taking standard PyTorch code and compiling it for the TPU. This translator is smart. It automatically fuses operations. Imagine a recipe. Instead of writing down mix, save, grab bowl, mix again, XLA groups all the mixing instructions together, saving trips to memory and boosting performance. If this translation bridges matures, the CUDA lock-in could rapidly evaporate. Google is also pushing JAX, a native language that handles massive model parallelism elegantly. If Meta shifts its core research to DAX, JAX, the threat becomes even more acute. Now, ultimately, this is an economic decision. The scale of generative AI means that unit economics, the total cost of ownership, TCO, now determines success. Nvidia sells its H100s at gross margins exceeding 75%. They are making super profits. Google, however, manufactures TPUs primarily at cost, which is their BOM plus R&D amortization. This allows Google to offer compute to Meta at a price point Nvidia simply cannot match without destroying its own margin structure. Now look at the power advantage. The 2x performance per watt efficiency of Google Ironwood translates to tens of millions of dollars in electricity savings annually for massive data centers. Google executives internally estimate that a successful adoption by Meta could capture up to 10% of NVIDIA's annual data center revenue, a swing of over $5 billion per year. Even if Meta does not switch entirely, this credible threat gives them immense negotiation leverage to demand major volume discounts from Nvidia, forcing them to compete on price for the first time. So, where is the market headed? It will likely fracture into two distinct halves. Now, the discovery AI, which is Nvidia's stronghold. So, this is the R&D stage. Training brand new, novel architectures will stick with Nvidia because of CUDA's flexibility. Then there is a factory AI. Now, once the model is stable, like a standard Llama transformer, and you need to deploy it at a massive scale, this is where superior unit economics of TPUs win. The rise of agentic AI that thinks over long periods and maintains long term state, is key here. These systems require massive context windows. For example, 10 million tokens for Llama. Google's Ironwood is perfectly positioned because its OCS interconnect allows the entire pod's 192 GB HBM to be treated as a unified memory pool. This is crucial for memory hungry, persistent AI tasks. So, what are the key takeaways? The deal between Meta, Google, and Oracle is a watershed moment. Does this mean that Nvidia is doomed? No. The risk is structural and financial, not existential. What is the financial risk? TPUs threaten to cap Nvidia's high gross margins by forcing them into price competition. And what's the structural risk? If the PyTorch XLA bridge achieves seamless portability, NVIDIA loses its strongest defense, which is the software moat. But the market is growing fast enough for both to thrive. We are moving from a single winner to two specialization lanes. NVIDIA remains the premium, versatile, the Ferrari of AI innovation and discovery. Google TPUs are becoming the highly efficient, industrial scale freight train of the inference economy. Ultimately, this competition is fantastic for everyone as it drives costs down and ensures AI intelligence is deployed everywhere. With that, we come to the end of the show. Support our work by joining us as a member. And thank you so much for watching. If you learned anything in this video, please like, share, and subscribe to the AI with Arun show. Thank you, and we'll be back soon.